Now we're going to turn to looking at the practical implementation of Voice over IP. And in this chapter, we're going to look at implementing Voice over IP over wide area networks. In other words, ignoring what's happening inside the building, we're going to look and see how you get the Voice over IP from one building to another. A private network is where you have dedicated capacity going point to point between your buildings. And one way to get this would be to get a dedicated T1 between every two buildings. So it would be a T1 going from A to B, one going from B to C, and another going from C to A. And of course, everything happens in both directions at the same time. Another way of getting dedicated capacity would be to use dark fiber, where you lease a fiber going between the buildings from another company, and you put your own lasers and photo detectors on there. But in both cases, you have guaranteed full-time capacity point to point between the buildings. Now, there's some pretty strong advantages to this. Perhaps the biggest advantage is that that's the highest QoS you can get, the highest quality of service from the network service provider. If you're getting T1s, what you're going to get is 1.5 megabits per second all the time, and with hardly any delay going from one end to another. There are no network slowdown stories happening here. The only way there would be a network slowdown is if you put too much traffic on your T1. But as far as the carrier is concerned, you're getting 1.5 megabits per second all the time, period, end of story. Now, besides the fact that this is the highest QoS you can get, the other main advantage is that you have total control. You decide what goes over this dedicated capacity and what comes out the other end and what you do with it. And since we have total control, then we can implement prioritization of voice. We can give voice higher priority than data, and since we have control of the story at both ends and it's just a pipe in the middle, we can actually make this be respected, and so we can guarantee voice quality because we can guarantee throughput and delays for voice packets. There are some advantages security-wise to this story because these are dedicated point-to-point capacities between your corporate locations. There are no 14-year-olds dialing into this story, hopefully. So it does have some better security aspects to it. From a cost point of view, there's a sales pitch here. If you have existing dedicated T1s between those buildings, then we might be able to think that we could use those T1s more efficiently by packetizing the voice instead of assigning channels to voice communications. Now, the cons, well, this is ridiculously expensive. I mean, how much do dedicated T1s cost from New York to Los Angeles? Well, if you got a really good deal on one, it might be $1,500 a month. That would be a good deal. More likely, we're talking $2,500 a month, month after month, year after year, for 1.5 megabits per second. Remember, LANs are going to be running at 1 gigabit per second. So that's 700 times slower than what LANs will be running at for $2,000, $2,500 a month. Also, dedicated circuits are highly inflexible. I mean, you get it all set up and working, and then you want to add another building. Well, you'd have to call up the service provider, have them rip out one connection, and add in 2 more dedicated lines. That'd cost you at least $1,000 in installation charges. It would take 4 weeks to get it installed. It wouldn't work. You'd have to call them, jump up and down, scream and shout. Finally, they get it all working, and then somebody wants to add another location. So this is very expensive and hard to add new locations. And then, as we discussed in the pros and cons chapter, the premise of the sales pitch that your existing dedicated lines can be used more efficiently, we want to take a look and see whether that's actually true or not, because the premise is that they're being underutilized. And what we might find, in fact, is that as the speeds of the data stuff grows to 1 gigabit per second on the LANs, that this 1.5 megabit per second connection is starting to look pathetically slow, and people are already complaining that it's too slow, so there are no efficiencies actually to be had. But this is one possibility for voice over IP long distance, is to do it over dedicated lines. And this is one of the few ways that we can currently guarantee the voice quality. Voice over IP over dedicated lines is not really where we're headed with this story. What we want to do is use a shared network, and so that some common carrier will deploy the network going to all sorts of different cities, and then we will pay to transmit information across it, and we'll end up sharing the capacity and the capital costs of putting all these points of presence and the equipment and the connections between them. We'll end up sharing that with lots of other users. And since they've got stuff deployed everywhere, then we can communicate to everywhere, and it's going to be cheaper and more flexible. We can add more connections if we want to. In the IP network world, the way that this is traditionally done is that a carrier will have a fiber optic backbone between major cities. They will use the SONET system to do automatic protection switching and alarming and maintenance and testing and all that sort of good stuff, and manage the bits on the fiber, and also channelize the bits into chunks of DS3s, like 45 megabits per second. Some of those DS3 rate connections on the fiber will be allocated to doing data services. The way that the carrier puts their data services onto this SONET fiber backbone is using a technology called ATM, asynchronous transfer mode. And so what they need to do is go purchase ATM switches and put them in their points of presence in each city, and then connect those ATM switches together with the SONET DS3 rate channels. And what the ATM switches do is they take everything that's coming in, whether it's IP packets or frame relay or some Ethernet type services, and takes those and chops them up into little 48-byte chunks and transmits them all interspersed across the DS3 rate channel to the ATM switch at the other end of the line, which then reassembles it into whatever it was, an IP packet, a frame relay frame, an Ethernet frame, and delivers it to the user on the far end. And so what they're doing is they're taking all of their data services and putting them together in an on-demand, statistically multiplexed one chunk of data after another fashion, using the backbone very efficiently. To build an IP network, what they would do is front-end all of this with some $20,000 routers from Cisco. So they would have this ATM over SONET fiber core, and then plugged into an ATM switch in one city would be an expensive router, and plugged into the ATM switch in the other city would be an expensive router, and this is presented to the user. So the carrier says, we've got an IP network service, and as far as the user is concerned, they need an access circuit to connect their router to the carrier's router, and they send IP packets over it. Unbeknownst to the user, those get chopped up into ATM cells and transmitted 48 bytes at a time to the far end router, which turns them back into IP packets, which delivers them to the user's router at the far end. So what we do here is we use SONET to manage the backbone and do automatic protection switching. We use ATM to multiplex all the data services together and do some quality of service things that we're going to look at later in this discussion. And then we front end it with IP, and IP is used to do the routing. And the way that that works is that we connect what are called permanent virtual circuits across the ATM between every two of the carrier's routers. So when you send a packet to the carrier's router, it looks at the IP address in the packet and it has to figure out which virtual circuit to take to get to the correct network